Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with number 39 in chapter 11 in the OER University textbook here. And what it says is, suppose we have a system of masses. Now I'm not going to write this all down. I just put here m sub I given in the problem. There's a picture right up above it similar to the one I have drawn. I went ahead and put the velocity vectors in blue. The distances, like this distance, all given in the picture. I'm not going to put that in my diagram just for this discussion. But so the masses are all given, the locations of these particles all given, and the velocities are all given in this problem. And then it says to calculate the angular momentum of each mass. So I'm going to go ahead and talk about how to do that. All right, so hopefully you've seen my video on angular momentum. Angular momentum is a vector quantity. It's equal to r times m times v. But the kicker is that the r has to be perpendicular to the v. So basically, you turn an angular momentum by taking a translational momentum, mv, and multiplying by the perpendicular distance. So let me talk about what that's going to look like in this problem. Take m1, for example. Here's m1, its velocity vector points to the right, and hence its momentum vector would be m1 v1, and it's to the right. If we multiply by this distance right here, we would have the angular momentum for that particle. So I'll go ahead and actually do particle 1. Its angular momentum is going to be, I'm going to call this distance y1. So it's going to be y1, given in the problem, times m1 v1. I'm grouping these together because it's distance, perpendicular distance, times the translational momentum. Now we got to decide on a plus or minus sign. In two-dimensional problems, counterclockwise or clockwise is good enough. So this guy's angular momentum is clockwise, so this would be some negative value. Doing counterclockwise positive. So just put in numerical values, get a number. These are all given in the problem, attach a minus sign to it. Particle 3, basically the same thing. The distance you need with particle 3 is this distance. Notice particle 4, the line of action goes right through the origin here. So I want you to think about, well, then what would the distance be to answer that question for particle 4? All right. Particle 2 here is the one that may give you a little bit of trouble. There are, first of all, let's talk about the velocity vector. Let's think about this in terms of components. I'm going to draw those in blue. You've got a v2x given in the problem, and a v2y given in the problem. They wrote that vector in unit vector form. v2, I'll go ahead and write it down. It's 3i minus 3j meter per second. I'll just put the units out here. So in this picture, that means that v2 is 3 meter per second right and 3 meter per second down. So just do this kind of in component form. Take v2x times this distance, and again, you know, v2x acts all along this line, so it's actually this distance to the line of action, and that angular momentum is going to be counterclockwise, so that's going to be positive. Then when you do the v2y, right, so you can think of that as acting along this line. The distance you need is here. And because this velocity vector is down, in a sense, that's a clockwise angular momentum. Right? So that's going to be negative in the sign convention. Right? So calculate the angular momentum of each particle individually and just keep track of them, clockwise versus counterclockwise. And you can do that either with these, like this, or by putting a plus and minus sign. But if you use plus and minus signs, make sure you define which way you're calling positive. When it says the total angular momentum of the system, just add those things up. Right? But remember, they have to be added vectorially, which means some of those will be positive, some negative. Right? I think that's probably enough to get you through that problem. I hope this helps. Have a great day.